Welcome back to Calm Psyche, where we wander gently through the mysteries of mind and cosmos, one slow breath at a time. Tonight, I invite you on a 2-hour journey, a soft, dreamlike exploration of paradoxes. These are the puzzles that twist logic into loops, the riddles that dissolve certainty, the questions that stretch your imagination until it feels like infinity itself is brushing against your thoughts. But don't worry, this isn't a test and you don't need to solve anything. In fact, paradoxes are beautiful precisely because they resist solving. They're like Zen gardens for the mind, endless patterns you can gaze at without needing an answer. Tonight, we'll wander through them slowly, letting their strangeness wash over us like waves. Think of this as a gentle paradox in itself, puzzles that are too interesting to ignore, yet told in a way that lulls you deeper into calm. A bedtime story that bends the mind, even as it soothes the heart. Over the next 2 hours, we'll meet famous paradoxes, the liar's paradox, where a sentence folds back on itself. Zeno's paradoxes, where movement seems impossible yet never stops. The Ship of Theseus, which asks whether a thing is still itself after every part is replaced. And Hilbert's Hotel, an infinite inn where every room is full, yet always has space for more guests. We'll wander into time travel contradictions, thought experiments with cats that are both alive and dead, and riddles of infinity that make the universe feel both too big and too close. Some paradoxes will sound playful, like brain teasers. Others will feel profound, touching the deepest mysteries of existence. All of them will carry you along on a river of quiet wonder. Before we drift too far, I'd love to know where you're listening from. Are you curled up in a quiet apartment in Tokyo, the city lights flickering far below? Are you stretched out on a couch in Toronto, letting the hum of traffic fade into background noise? Or maybe you're listening from a small village, where the only sound outside is the chorus of crickets. Wherever you are, you're part of this moment, part of this gentle gathering of minds across the globe, linked by curiosity and calm. And as always, remember, this journey is for education and relaxation only. I'm not here to give medical advice or replace any kind of professional care. Think of me instead as a soft voice in the dark, walking beside you as we wander into the strange and beautiful. So settle in, take a slow, deep breath, let your shoulders drop. You don't need to stay alert. You don't need to remember everything. Just let the words float past like lanterns in a night sky. Some will glow brightly for a moment, others will drift away into silence. All of them will carry you deeper into the space between thought and dream. Ready? Then let us begin. What exactly is a paradox and why do they bend our minds so easily? That's where our journey starts. So, what exactly is a paradox? On the surface, a paradox is a kind of puzzle, a statement, idea, or situation that seems to contradict itself, but somehow still carries truth. It's like a doorway that opens onto another doorway, which leads back to the first. You can walk forever and never reach the end. At first glance, paradoxes may sound like mistakes, like errors in reasoning. But look a little closer, and you find there's something else entirely: invitations. Paradoxes invite us to question the rules we assume about reality. They don't give us neat answers, they give us a mirror, one that shows how strange our thinking really is. The word itself comes from the Greek paradoxon, meaning contrary to expectation. That's the heart of it. A paradox unsettles the mind because it doesn't behave the way it should. It's the itch you can't quite scratch, the riddle that refuses to let you box it in. There are many types of paradoxes, and tonight we'll meet several of them. Some are logical paradoxes, like the liar's paradox. This sentence is false. If it's true, then it's false. But if it's false, then it must be true. It loops endlessly like a snake swallowing its own tail. Others are mathematical paradoxes, like Hilbert's Hotel or the Banach-Tarski paradox, where infinity itself bends the rules of space and number. Then there are physical paradoxes, where the laws of physics seem to contradict themselves. Schrödinger's cat, both alive and dead, or the twin paradox of relativity, where two people can live the same time so differently. There are even philosophical paradoxes, which reach into ethics and existence. If an all-powerful being exists, can they make a stone so heavy they cannot lift it? If tolerance is unlimited, does it destroy itself? These are not riddles with clean solutions, but doorways into deeper reflection. Paradoxes feel uncomfortable because they expose the limits of our frameworks. We want the world to be consistent, logical, and tidy. Paradoxes whisper that maybe it is, or maybe it is, but our minds aren't yet big enough to see the whole picture. And here's something soothing to consider. Paradoxes are not problems to be solved, but companions to be lived with. They're the universe's way of reminding us that knowledge is infinite, and that even in our greatest insights, mystery still waits. Think of a paradox like a koan in Zen practice, a question designed not to be answered but to dissolve your need for answers. What is the sound of one hand clapping? It's not meant to be solved. It's meant to stretch you into silence, into wonder, into peace. Tonight, as we drift through paradox after paradox, I invite you to hold them gently. Don't wrestle them to the ground. Don't force them to give you closure. Instead, let them circle in your mind like soft waves. Let them unsettle you just enough to loosen the grip of ordinary thought. And when your mind gets tangled, when the loops start looping inside loops, take a breath and smile. That's the paradox doing its work. Paradoxes remind us that certainty is overrated, that not knowing can be beautiful, and that sometimes the truest wisdom is the ability to rest in the unresolvable. And so, with that understanding, let's step into our first paradox, one of the oldest, simplest, and yet most baffling. A sentence that cannot sit still, a riddle that eats itself. The liar's paradox. The liar's paradox, this sentence is false. Let's begin with a simple sentence, just 6 words. This sentence is false. At first it seems harmless, almost playful, but then your mind tries to make sense of it. If the sentence is true, then what it says must be the case. The sentence is false. But if it's false, then what it claims isn't true, which means the sentence is true. Back and forth endlessly like a pendulum that never settles. This is known as the liar's paradox, one of the oldest recorded paradoxes in philosophy. Its origins are often traced back to the Greek philosopher Eubulides of Miletus, around the 4th century BCE. He posed the riddle. A man says that he is lying. Is what he says true or false? It seems like a trick of words, but it goes deeper than that. The liar's paradox challenges the very way we use truth and logic. We like to imagine that every statement can be neatly labeled, true or false, yes or no. But here, those categories collapse. The sentence resists classification, twisting our labels into knots. You can picture it like 2 mirrors facing each other. You look into one and see an infinite hallway of reflections, stretching away without end. The liar's paradox is the mind's version of that. Truth reflecting falsehood, reflecting truth, reflecting falsehood, until your thoughts drift into infinity. Philosophers, logicians, and mathematicians have wrestled with this paradox for centuries. Some argue that such sentences are meaningless, broken loops of language that we should simply set aside. Others suggest they reveal something fundamental about the limits of logic itself, that even the most careful systems of truth have boundaries they cannot contain. In modern times, the liar's paradox has found its way into mathematics and computer science. When we design logical systems or even write computer programs, paradoxes like this can cause breakdowns, infinite loops that never resolve, errors that crash the system. In a sense, the liar's paradox is like a bug in reality's code, a whisper that no framework can ever be complete. But tonight, you don't need to solve it. You don't need to take sides in the debate. Instead, you can let it unfold like a puzzle box you never have to close. Imagine lying in bed, whispering to yourself, "This sentence is false." Each time you think you've pinned it down, it slips away like trying to catch smoke. Instead of growing frustrated, let yourself smile. The paradox isn't there to be solved, it's there to remind you of the strangeness of thought itself. There's something deeply soothing about that realization. Not everything has to fit. Not everything has to be boxed up and labeled. Some things are allowed to remain mysterious, looping forever. As you drift with this paradox, feel how it loosens the grip of logic. Your mind, so used to chasing answers, begins to soften. The liar's paradox becomes a lullaby of contradiction, rocking you gently between true and false, yes and no, until the categories blur and fade into calm. In the end, the liar's paradox is less of a riddle and more of a mirror. It shows us that truth itself is more slippery than we like to admit. It invites us to rest in that slipperiness, to be at peace with uncertainty. And in that peace, paradox becomes not a frustration but a friend. And so, with your mind now softened by this first loop, let us move forward to a set of paradoxes that are older still, crafted by a philosopher who used them to challenge the very idea of motion itself. Let us meet Zeno's paradoxes, Part I, Achilles and the Tortoise. Picture this. The great hero Achilles, swift-footed and nearly invincible, lines up for a race. Beside him is his unlikely opponent, a humble tortoise. To make things fair, the tortoise is given a head start. Let's say 100 paces. The race begins. Achilles charges forward, each stride carrying him closer to the tortoise. Surely he will pass it in moments. But then the philosopher Zeno of Elea, living in the 5th century BCE, whispers something strange. No matter how fast Achilles runs, he can never truly overtake the tortoise. At first this sounds absurd. Of course he can, but Zeno invites us to look closer step by step. Before Achilles can reach the tortoise, he must first cover the 100 paces between them. While he does that, the tortoise has moved a little farther ahead. Next, Achilles covers that smaller distance. But in that time, the tortoise moves forward again, just a tiny step, but still ahead. Every time Achilles closes the gap, there's still a smaller gap left. An endless sequence of distances, each shrinking but never quite gone. And so, by Zeno's logic, Achilles never passes the tortoise. He approaches forever but overtakes never. This is Zeno's paradox of motion, a thought experiment that challenges the very idea of movement. It tells us that even something as simple as running a race is woven from infinite steps, infinite divisions of time and space. Of course, in the real world, Achilles would win. He would pass the tortoise easily. But Zeno's paradox isn't meant to stop races, it's meant to stop us. To make us pause and ask, how can infinite steps fit inside a finite race? How can endless divisions add up to a single moment? Later, mathematicians would explain it using the concept of infinite series. Each smaller distance Achilles runs, half the gap, then half again, adds up to a finite total. Infinity, it turns out, can be summed. But Zeno, without modern math, left the puzzle hanging in the air, a riddle for the mind to circle forever. There's something soothing in imagining Achilles and the tortoise frozen in this paradox. Achilles, forever running but never catching. The tortoise, forever plodding but never overtaken. An endless chase across an endless road, time stretched thin like silk. As you drift tonight, you might feel a little like Achilles, always moving toward rest but never quite arriving. Each breath carries you closer. Each thought fades a little more. And though the finish line feels distant, it is already here, waiting in the infinite sum of small steps. The paradox is not a failure of motion. It is a mirror of infinity. It reminds us that every journey, no matter how vast, is made of endless little moments. Every heartbeat, every blink, every breath is a step in the race. And somehow, miraculously, all those infinite steps carry us home. So let Achilles keep running. Let the tortoise keep walking. In their endless dance, we find a strange kind of peace. The comfort of infinity stretched into a path we can walk, slowly, gently, forever. And as Achilles takes his eternal strides, we move to Zeno's second puzzle. one where time itself seems to freeze, and an arrow never reaches its mark. Zeno's Paradoxes, Part II, the arrow that never moves. Imagine an archer, bow drawn, string trembling. The arrow is released, slicing through the air toward its target. To our eyes it is swift, smooth, unstoppable. But to Zeno of Elea, something far stranger is happening. Zeno asks us to pause the world to freeze the arrow in flight at a single instant of time. At that instant, the arrow is not moving forward. It simply occupies a single position, suspended in space. After all, motion requires change, and in this frozen moment there is none. Now imagine dividing time into smaller and smaller instants. Every moment is frozen, every instant shows the arrow still. If at every instant the arrow is at rest, then when does it ever move? Add up all those moments of stillness, and paradoxically you get stillness. According to Zeno, the arrow never moves at all. This is known as the arrow paradox. It's simple, almost childlike in its reasoning, yet deeply unsettling. How can something be both in motion and not in motion? How can time, made up of frozen slices, create the flow we experience? Zeno's challenge forces us to question whether time is continuous or made of discrete units. Is it like a river, flowing smoothly, or like a film reel, made of countless still frames shown so quickly that our minds create the illusion of motion? Modern physics still wrestles with versions of this question. At the quantum level, time and space might not be infinitely divisible. There may be a smallest unit, a tick of time, a grain of space, below which the idea of motion doesn't even apply. The arrow paradox lingers, reminding us that even in the age of mathematics and relativity, the nature of time remains mysterious. But here in the quiet of night, we don't need equations. We only need imagination. Picture the arrow suspended in the dark, each moment frozen like a photograph, a sequence of stillness that somehow creates flight, a paradox that whispers. Perhaps motion is an illusion, a trick of perception, a dream. And yet paradoxes are gentle teachers. Even if the arrow is never moving, it still strikes the target. Even if time is made of frozen moments, we still feel its flow. The contradiction does not stop the world, it only deepens its mystery. As you breathe slowly now, feel how your breath is both stillness and motion. In every instant, your body simply is. And yet, across those instants, the rise and fall of your chest becomes a rhythm, a flow, just like the arrow, just like time. Zeno may have meant his paradoxes as arguments against the possibility of change. But tonight, they become something else, reminders that reality is more subtle than it appears, that even the simplest things, a race, an arrow in flight, the passing of time, hide infinities within them. And so we leave the arrow suspended in the quiet air, caught forever between stillness and motion, between logic and mystery. From here, our path leads to another paradox, not about motion, but about identity itself. A riddle that asks, when does something stop being what it is? The Ship of Theseus, when does a thing stop being itself? Long ago in the myths of Greece, there was a hero named Theseus. His ship, used to carry him back from his great adventures, became a cherished symbol in the city of Athens. For generations, it was preserved in the harbor. Whenever a plank grew old and rotten, it was replaced with a fresh one. When the sail tore, it was mended. When the mast cracked, it was swapped for new timber. Over time, the ship changed, slowly, quietly, piece by piece. Centuries passed, and every part of the ship was replaced. Not a single plank or nail remained from the original vessel that carried Theseus. And so the philosophers asked, is it still the Ship of Theseus? If identity is tied to material, then perhaps not. The old wood is gone, replaced entirely. But if identity is tied to form, function, and memory, then perhaps yes. It looks the same, it serves the same purpose, and the people of Athens call it the same ship. The paradox deepens with a twist. Imagine someone had gathered all the discarded pieces of the original ship and rebuilt it, plank by plank, mast by mast. Now there are two ships, one made entirely of replacement parts, the other made entirely of the original wood. Which is the true ship of Theseus? This riddle has no simple answer, which is why it has endured for thousands of years. It forces us to confront the question, what makes something itself, its material, its continuity through time, or our perception of it? We can see echoes of the paradox everywhere in life. Your body, for instance, replaces its cells constantly. Skin cells last weeks, blood cells months, even your bones renew over the course of years. In a sense, you are not made of the same matter you were 10 years ago, yet you remain you. Is identity something deeper than material? Perhaps it lies in memory, or in the pattern of your mind, or in the story others tell about you. Perhaps, like the ship of Theseus, you are a vessel continually rebuilt, yet somehow always the same. The paradox also reaches into modern questions, in technology. For example, if you replace every part of a computer, is it still the same computer? If you copy all the data into a new machine, is that the same machine or just a clone? In neuroscience, if a human mind were perfectly replicated thought by thought, would that replica be the same person? As we drift with Theseus's ship tonight, let it carry us gently into reflection. You are a collection of changing parts, cells, atoms, memories, yet you feel continuous. You wake up each day in a body both new and old. Like the ship, you are both the same and not the same. There's comfort in this paradox. It tells us that change does not erase identity, that renewal is not loss, that even as parts of us fade and are replaced, there is still a thread that carries us forward, like a ship sailing steadily across the ocean of time. So imagine Theseus's ship rocking quietly in the harbor, planks creaking, sails sighing in the wind. Whether it is old or new, original or rebuilt, it floats. It carries its story. And like that ship, you drift gently, unchanged in your essence, even as the world remakes you in small, quiet ways. Next, we will explore a paradox of perception, one that asks whether the world you see is truly there, or if it vanishes the moment you stop looking. The paradox of perception. Does the moon exist when you're not looking? Tonight, let's play a gentle game of hide-and-seek with the universe itself. It begins with a simple, unsettling question. Does the world exist when no one is watching it? At first, the answer feels obvious. Of course it does. The moon still glows in the sky whether we see it or not. The ocean still crashes against the shore when no one is listening. The forest still grows when no eyes rest on it. The universe doesn't care whether we're awake or asleep, or does it? This question haunted philosophers for centuries. In the 18th century, the thinker George Berkeley suggested something astonishing. Objects exist only as they are perceived. To exist is to be experienced. A tree, a mountain, even the moon itself is only real when it is seen, touched, or sensed. Without perception, they are not merely hidden, they vanish into nothing. Imagine walking into an empty room and seeing a chair. Now leave the room and close the door. Does the chair continue to exist when you are gone? To Berkeley, the answer was no. The chair lives only in perception, and without an observer, it is nothing. Of course, this leads to an uneasy thought. How does the world persist when no human sees it? Berkeley answered with a radical idea. The universe continues only because it is always perceived by God. The divine gaze ensures that everything remains in place when human eyes look away. Later, physics added its own strange twist. In the 20th century, the birth of quantum mechanics revealed that particles, the tiniest bits of reality, don't seem to have definite positions until they are observed. In the famous double-slit experiment, particles behave like waves when unmeasured, spreading out in possibility. But when observed, they collapse into a single state. Observation changes reality. This led to the famous question attributed to physicist Albert Einstein. Does the moon exist only when I look at it? Modern science doesn't take Berkeley's view literally. The moon does not blink in and out of existence with each glance, but the paradox of perception remains. At the smallest scales, the act of measurement of awareness seems to shape what is real. Reality may not be fixed and solid but dependent, in some way, on observation. Now imagine drifting in your bed, the room dark and still. The objects around you, the lamp, the table, the walls, fade as your eyes close. In your mind they dissolve into absence, yet you trust they are still there, waiting for morning light. Perhaps this trust is what anchors the world. Or perhaps, like the philosophers and physicists suggest, the universe is stranger, less certain, more dreamlike than we dare to admit. The paradox of perception is not meant to frighten but to soften the edges of reality. It whispers that the world is not a rigid machine but a dance between observer and observed. You are not separate from the universe. You are part of the act that sustains it. Every glance, every breath, every awareness is a thread in the fabric of existence. So as you let your eyes grow heavy, think of the moon high above. Whether you watch it or not, it hangs there in the night sky, pale and constant. Or perhaps it flickers gently into being only when you remember it. Either way, it is enough. From here, our path drifts into another paradox, one of infinity itself. A puzzle that turns an ordinary hotel into a place that can never, ever be full. Hilbert's Hotel, a guest house for infinity. Imagine a quiet evening walk, and as you turn a corner you find a hotel glowing softly in the night. Its sign reads, Hilbert's Hotel, always room for one more. At first glance it looks ordinary, a lobby with potted plants, a clerk at the desk, an elevator humming in the background. But this hotel is different. It has an infinite number of rooms. Room 1, Room 2, Room 3, the numbers stretch forever down endless hallways. Every room is occupied. There is no vacancy sign glowing. Yet somehow there is always space for one more guest. This is the Hilbert Hotel paradox, imagined by mathematician David Hilbert in the early 20th century. It is a thought experiment designed to reveal the strangeness of infinity. Here how it works. Suppose a new traveler arrives asking for a room. The hotel is full, but the clerk smiles and says, "Of course we can accommodate you." He picks up the phone and calls every guest. "Please move from your current room number N into room number N+1. Room 1 moves to room 2, room 2 to room 3, room 3 to room 4, and so on. Suddenly, room 1 is free for the newcomer, and every other guest still has a room. Infinity has stretched itself effortlessly to make space. Now suppose a bus arrives carrying an infinite number of guests. Impossible, not here. The clerk nods and says, "No problem." He calls again. "Everyone, please move from room N to room 2N. Guest in room 1 moves to room 2, guest in room 2 moves to room 4, guest in room 3 to room 6, and so on. Now all the even-numbered rooms are filled, and all the odd-numbered rooms are free, an infinite number of spaces for the new arrivals. Hilbert's Hotel shows us something strange. Infinity is not like ordinary numbers. A finite hotel cannot accept guests when it is full, but an infinite hotel, even when full, can always stretch further. This paradox is more than a playful story. It touches the very core of mathematics and cosmology. Can actual infinities exist in the physical universe? If the cosmos is infinite, is it like Hilbert's Hotel, always expanding, always accommodating? Or is infinity only a mathematical dream, too strange for the real world? As you imagine the endless halls of Hilbert's Hotel, picture yourself walking quietly down a corridor. The numbers on the doors rise higher and higher. Room 10, room 100, room 10,000, room 10 billion. They never end. The hallways stretch forever, yet each room is small and ordinary, with a bed, a lamp, and perhaps a window looking into endless night. It's soothing in a way. Infinity sounds overwhelming, but here it is dressed in soft carpets and golden lamps, made gentle and familiar. A reminder that the infinite does not always roar. Sometimes it whispers in quiet paradoxes. Hilbert's Hotel does not solve infinity, but it makes us smile at its absurdity. The hotel is always full, yet never full. Always finite in each step, yet infinite in its reach. Like time, like space, like the mind that drifts now towards sleep. And when you close your eyes tonight, perhaps you will find yourself in one of its rooms, room 7, or room 77, or room 7 trillion, resting quietly in the infinite guest house of dreams. Next, we journey deeper into infinity with another paradox, one that asks, if you try to walk across a room by always going halfway, will you ever reach the other side? The dichotomy paradox, can you ever reach the end? Picture yourself standing at one end of a long, quiet hallway. At the far end is a soft, glowing door, your destination. You take a breath and begin walking, but before you can reach the door, you must first reach the halfway point. That's simple enough. Now, from that halfway point, you must walk halfway again, then halfway again. Each step cuts the distance smaller, but there is always another halfway to go. This is Zeno's dichotomy paradox, one of the most famous puzzles of motion. It tells us that to reach the end, we must first complete an infinite number of tasks, reaching half the distance, then half again and again without end. If there are infinitely many steps, how can we ever arrive? And yet in the real world we do. You can cross a hallway. You can walk across a room, a street, a field. Achilles does overtake the tortoise. An arrow does reach its target. So where does the paradox live? It lives in the gap between logic and experience, between the infinite and the finite. Mathematically, the answer lies in the idea of converging series. Imagine adding numbers like this: 1 2 plus 1 4 plus 1 8 plus 1 16. The sequence continues forever, but the total approaches 1. Infinity hides inside these fractions, yet their sum remains finite. In the same way, the infinite steps of the dichotomy paradox add up to a finite journey. But when Zeno first posed this riddle 2,500 years ago, the mathematics of convergence had not yet been invented. To him and his listeners, the paradox was not a problem to solve, but a mirror held up to motion itself. How can we live in a world that seems simple and continuous, yet is composed of infinite divisions? The dichotomy paradox doesn't just live in philosophy, it echoes in our daily lives. Think of all the goals we set: finishing a book, building a career, even finding rest at the end of a long day. Each goal can be broken into smaller steps, and those steps into even smaller ones. Sometimes it feels as though there is no end, only more halves to reach, more tasks to complete. And yet, like the walker in the hallway, we arrive. Not because the steps end, but because the infinite hides quietly within the finite, folded like origami. Every moment you breathe is an infinite paradox resolved into a single heartbeat. Every step you take is an infinity collapsed into motion. Let's soften this thought into something more dreamlike. Imagine yourself shrinking smaller and smaller as you walk toward the glowing door. Each halfway mark makes you lighter, slower, more delicate, until you feel as though you are gliding rather than stepping. The infinite halves unfold endlessly, and yet somehow you find yourself at the door, hand on the handle, paradox resolved. The dichotomy paradox whispers something profound. Infinity is not always vast. Sometimes it hides in the simplest actions, like walking across a room. Sometimes the infinite lives not in the stars but in the space between steps. And so, as you drift tonight, think of every breath as its own infinity, divided endlessly but lived wholly. The destination is always reached, not because the halves disappear, but because you are carried through them gently, step by step. Next, we'll move from the endless hallway to a new paradox, one where a single question about probability leaves us stranded in a world of chance. The famous Monty Hall problem. The Monty Hall paradox: should you switch doors? Imagine you're standing under bright studio lights. The crowd claps softly in the background, and before you are 3 large doors. Behind one is a car, shiny, sleek, the prize everyone hopes for. Behind the other 2 are goats, calm and chewing hay. The host, smiling warmly, asks you to choose. You point to a door, let's say door number 1. Now the host, who knows what's behind every door, opens one of the others, let's say door number 3. Behind it is a goat. The host then turns back to you with a grin and says, "Do you want to stick with your choice or switch to door number 2? It seems like a fair coin flip now. 2 doors remain. One has a car, one a goat. Surely it's 50-50, right? But here is the paradox. If you switch, your chances of winning double. At first glance, this feels like a trick. How can switching matter? But let's walk through it slowly. When you made your first choice, the probability of picking the car was 1 in 3. That means the probability of picking a goat was 2 in 3. The host's action doesn't erase those odds, it just reveals one of the goats. If you stick with your original door, your chance of winning is still 1 in 3. But if you switch, you now inherit the 2 in 3 chance that you had originally picked a goat. Switching, strangely, gives you better odds. This puzzle, called the Monty Hall paradox after a real game show host, is one of the most famous counterintuitive problems in probability. Even professional mathematicians have argued fiercely about it. When Marilyn Vos Savant explained it in a newspaper column in the 1990s, thousands of readers wrote letters of protest, insisting she was wrong. But careful simulations and logic prove her right. Switching doors doubles your chance of winning. Why is it so unsettling? Because our intuition about probability is weak. We trust our gut to tell us what's fair, but the math hides deeper patterns. The Monty Hall paradox teaches us that what seems like a simple choice can hide layers of subtlety. Reality doesn't always match our instincts. And like many paradoxes, this one has a dreamlike quality. Imagine the doors stretching into infinity, endless choices in an endless hallway of games. Each time the host pulls back one curtain, reveals one goat and asks, "Will you stay, or will you switch?" It becomes less about cars and goats and more about life itself. How many times have you faced choices that seemed equal but where hidden information tipped the scales? How many times have you trusted instinct when the deeper truth required patience, reasoning, or the courage to switch paths? As you rest tonight, think of the doors as possibilities in your own life. Some open to disappointment, others to unexpected treasures. The paradox doesn't tell you which to choose, but it reminds you that intuition alone can be misleading. Sometimes wisdom lies in pausing, in reconsidering, in daring to change the door you first picked. The Monty Hall paradox is not just about games. It's about perspective, about how reality shifts when we notice what is hidden. And in that shift, we discover that the world is not always what it seems, but always deeper, stranger, more surprising than we expect. From here, our journey takes us into another paradox, one where cutting a ball into pieces somehow creates not one ball, but 2, each the same size as the original. A puzzle so strange, it feels like sorcery. The Banach-Tarski paradox, a universe from a ball. Picture this, a simple, solid ball resting quietly on a table, ordinary, unassuming. Now imagine slicing this ball into a handful of pieces, not with a knife but with the strange, invisible scalpel of mathematics. You rearrange those pieces carefully, and suddenly, impossibly, you find you've created not just one ball but 2, each identical in size to the original. This is the Banach-Tarski paradox, one of the most bewildering results in modern mathematics. It tells us that, under certain rules, it is possible to take a solid sphere, divide it into a finite number of parts, and reassemble those parts into 2 spheres the same size as the original. No shrinking, no stretching, no adding material, just rearrangement. At first, this feels like pure magic. How can one ball become 2 without breaking the laws of physics? Does this mean we could duplicate gold, food, or even planets? Not quite. The paradox is a product of pure mathematics, not physical reality. It depends on abstract concepts like the axiom of choice, which allows us to select elements from infinitely many sets in ways that defy ordinary intuition. The pieces created in Banach-Tarski are not pieces you could ever hold or even describe clearly. They are infinitely complex, dust-like fragments that only exist in the strange landscape of mathematical possibility. To human senses, they are unimaginable. To the rules of math, they are perfectly valid. And so the paradox stands. One ball becomes two. Infinity is smuggled inside the finite. Creation emerges without effort. It is unsettling, isn't it? To think that beneath the everyday solidity of the world lies such strangeness. That logic itself can produce outcomes that look like sorcery. But there is also wonder here. The Banach-Tarski paradox reveals that mathematics is not just a tool for measurement. It is a universe of imagination, where impossible things can happen without breaking a single rule. As you drift tonight, think of that ball on the table. In your mind, see it dividing softly, silently, like mist dispersing into the air. The fragments twist and shimmer, rejoining not into one ball but into two, both whole, both identical. The table does not protest. The room does not change. Only the laws of mathematics smile, reminding us how strange infinity can be. This paradox whispers of abundance, of the possibility that more can come from less, that reality may not always obey the limits we imagine. It is a riddle not just of numbers, but of imagination itself. And so, we leave the ball resting quietly once more, its twin beside it, both glowing softly in the dreamlike light of paradox. Next, we'll wander into a puzzle of time, one where traveling to the past tangles us in contradictions. A paradox not of space or matter, but of causality itself. The grandfather paradox: can you change the past? Imagine you build a time machine. It hums quietly in your room, a doorway through which yesterday waits like a hallway you can simply walk down. You step inside, twist the dial, and suddenly find yourself decades in the past, long before your own birth. And now comes the unsettling thought experiment. What if you were to meet your grandfather before he had children? What if, for some reason, you prevented him from ever becoming a parent? The paradox unfolds instantly. If your grandfather never has children, then your parent is never born. And if your parent is never born, then you are never born. But if you are never born, you cannot travel back in time. And if you cannot travel back in time, then your grandfather does have children, your parent is born, and you exist after all. The paradox loops endlessly. The very act of changing the past erases the conditions that allowed you to change it. This is the grandfather paradox, perhaps the most famous thought experiment about time travel. It exposes the contradictions that arise when we imagine tampering with causality, the chain of cause and effect that normally keeps reality stable. Philosophers and scientists have wrestled with this puzzle for generations. Some argue that the paradox proves time travel into the past is impossible. Others suggest alternative explanations. One possibility is the idea of consistency constraints, that the universe, like a careful storyteller, will not allow contradictions. You might travel to the past, but whatever you do will always fold back into history in a way that preserves your existence. If you try to prevent your grandfather from having children, circumstances will conspire against you. The gun jams, the car breaks down, chance events intervene. You cannot erase yourself because the story of reality does not permit it. Another possibility is the multiverse theory. In this view, when you change the past, you do not alter your own timeline. Instead, you branch into a new one. If you prevent your grandfather from having children, you simply create a parallel universe in which you were never born, but you still exist in the original timeline, unaffected. Both explanations soften the paradox, but neither erases its haunting quality. The grandfather paradox reminds us that causality, the idea that the past shapes the present and the present shapes the future, is fragile. Time, which feels like a steady river, may not be so simple. And yet there is something soothing in imagining time loops as you drift tonight. Imagine yourself stepping into that humming machine, traveling backward, watching history unfurl in reverse. The sun rises in the west, rivers flow uphill and leaves leap from the ground back into trees. The paradox curls around you like a blanket, impossible, yet comforting in its strangeness. Perhaps the grandfather paradox is less about physics and more about our longing, the desire to change what has already been, to mend mistakes, to undo pain, to reach back into memory and rewrite the script. But paradox whispers gently, the past is not clay, it is glass. Once shaped, it cannot be remolded, only seen, remembered, reflected upon. And so, we leave the time machine glowing softly in the night, a doorway into contradictions. From here, our next journey will not take us backward but forward into a future where prediction itself becomes a trap. A paradox where knowing tomorrow changes tomorrow, and knowledge twists fate into knots. The prediction paradox: can you know the future without changing it? Picture this. You are sitting in a quiet room, and a mysterious visitor places a sealed envelope on the table in front of you. Inside, they say, is a prediction of your exact actions for the next 24 hours. Every decision, every word, every hesitation already written down. You feel the weight of the envelope, and curiosity builds like pressure. Could it really be possible to know the future with such precision? Suppose you open the envelope. You read that in 10 minutes you will drink a glass of water, but immediately a rebellious spark flickers inside you. You decide you won't drink. You'll resist just to prove the prediction wrong. You cross your arms determined. But as the minutes tick by, your throat feels dry. Your thoughts fixate on water. Finally, frustrated by your own stubbornness, you grab the glass and take a sip. The prediction was right after all, not in spite of your resistance, but because of it. This is the essence of the prediction paradox. If the future can be known in advance, does the very act of knowing change the outcome? And if so, was the future truly predicted? Or did the knowledge itself become part of the cause? Philosophers often compare this to the ancient idea of prophecy. In myths, oracles would predict a hero's fate, but often it was the hero's attempt to avoid the prophecy that caused it to come true. The future seemed fixed, yet the knowledge of it was inseparable from the chain of events that unfolded. This paradox also touches modern science, especially in fields like quantum physics and chaos theory. At the tiniest scales, particles behave unpredictably. In chaotic systems like the weather or human behavior, small differences grow into massive changes. The future can be influenced by the tiniest nudge, including the act of observing it. So can the future ever truly be predicted? If the universe is deterministic, then yes. Every atom follows the laws of physics, and in principle, the future is already written. But if the universe is indeterministic, governed by chance, quantum uncertainty, and chaos, then the future is open, branching like a tree in the wind. The paradox rests in between. Perhaps even if the future could be known, the knowledge of it would alter behavior in ways that fold back into the prediction. The act of knowing becomes part of the loop. As you drift tonight, imagine that sealed envelope resting on your nightstand. Inside, every detail of tomorrow waits silently. Would you open it? Would you want to know? Or would you let it remain sealed, a secret the universe keeps for itself? The prediction paradox whispers a gentle reminder. The unknown future may be kinder than the one we try to control. To predict is to interfere, but to accept is to be free. And so we close the envelope, set it aside, and let the night cradle us. In the next section, we'll wander into an even stranger puzzle, a paradox of motion, where crossing even the simplest distance becomes impossible when sliced into infinity. The bootstrap paradox, information from nowhere. Imagine you are sitting at your desk late at night, papers scattered, coffee cooling, when suddenly, as if out of nowhere, a thick, leather-bound book appears on the table. You open it. The book is filled with diagrams, notes, and instructions for building a time machine. The handwriting feels oddly familiar, but you cannot place it. You follow the directions, piece by piece, and to your amazement the machine works. You climb inside, twist the dials, and leap backward in time. On a whim, you leave the book, the very one you had been studying on your younger self's desk before returning to the present. Here lies the paradox. Where did the book come from? It wasn't written by you because you only received it. It wasn't written by your younger self because they too merely received it. The book has no true origin. It exists in a closed loop, passing endlessly through time, uncreated yet always present. This is the bootstrap paradox, named after the old phrase to pull oneself up by one's bootstraps, to accomplish something impossible by using one's own effort. Here, information, objects, or even people seem to appear from nothing, sustained by a loop in time. Science fiction loves this paradox. A musician learns a famous melody from a mysterious stranger, only to later become the composer who teaches it to their younger self. A scientist receives schematics for a machine, builds it, then travels back to hand themselves the schematics. A traveler gives Shakespeare a copy of his plays, and suddenly Shakespeare never writes them. He only copies them from the book. But the unsettling truth is this: the paradox is not just fantasy. In principle, according to some interpretations of physics, closed time-like curves, paths through spacetime that loop back on themselves, might be possible. General relativity does not forbid them entirely. If they exist, the bootstrap paradox could be more than just a story. And if so, what does it mean for causality? Normally, we expect every effect to have a cause and every cause to follow from something before it. But in a bootstrap loop, the chain closes on itself. There is no first link. The book is never written. The song is never composed. The invention is never invented. Yet they exist anyway, circling endlessly like a snake swallowing its own tail. For the human mind, this is deeply unsettling. We crave origins. We want to know where things begin. But paradox whispers, sometimes there is no beginning, no first spark. Sometimes the loop is the whole story. As you drift tonight, imagine that book again, resting on the desk. Its cover glows faintly in the dim light, its pages heavy with knowledge from nowhere. You cannot trace its history because it has none. It exists only in the strange dance between past and future, between giving and receiving, forever locked in a cycle. Perhaps in a way, the bootstrap paradox mirrors the universe itself. Where did existence come from? What sparked the first star, the first atom, the first thought? We search for origins, but maybe reality itself is a loop, a self-contained mystery that requires no outside cause. The paradox does not solve the question, but it soothes it like a lullaby sung in a circle, without beginning or end. And so the book rests, the machine hums, time folds, and we gently drift onward. In our next section, we will leave time behind and step into a paradox of knowledge and belief, where truth and lies tangle into contradictions, and even the simplest statement can undo itself. The Fermi paradox: where is everybody? On a summer afternoon in 1950, the physicist Enrico Fermi sat at lunch with his colleagues in Los Alamos. The conversation turned to the possibility of intelligent life beyond Earth. The universe, after all, is vast. Hundreds of billions of stars in our galaxy alone, many with planets. With so many chances for life, someone surely must be out there. Fermi paused, thoughtful, then asked a question so simple it still echoes through science and philosophy. Where is everybody? This is the heart of the Fermi paradox. The contradiction between the high probability of extraterrestrial civilizations and the striking absence of evidence for them. Think of it this way: our Milky Way is more than 13 billion years old. Even at slow speeds, a civilization with advanced technology could explore the entire galaxy in a fraction of that time. Signals, probes, even faint traces of life, all should be visible by now. And yet, when we listen, the cosmos is quiet. The paradox deepens as we imagine the numbers. Astronomers estimate there are perhaps 100 billion stars in our galaxy, many with Earth-like planets in habitable zones. If even a tiny fraction of those worlds spawned life, and an even smaller fraction produced intelligence, then we should be surrounded by alien civilizations. The galaxy should shimmer with evidence, but it does not. So where are they? Some answers are hopeful. Perhaps life is rare, and Earth is one of the lucky few. Perhaps civilizations exist but are too far away, or their signals too faint for us to detect. Perhaps they are cautious, watching quietly, choosing not to reveal themselves, the so-called zoo hypothesis, in which we are animals in a cosmic reserve, observed but untouched. Other answers are darker. Maybe intelligent life tends to destroy itself through war, ecological collapse, or unchecked technology. Perhaps civilizations rarely last long enough to spread among the stars. This is known as the Great Filter, the idea that somewhere between the birth of life and the rise of star-faring civilizations, there is a near-impossible hurdle. We do not know if humanity has already passed that filter, or if it still lies ahead. The paradox stirs something deep within us, the loneliness of an empty sky. To imagine we might be the only intelligent beings in the galaxy is at once humbling and terrifying. If true, it makes us rare beyond measure, precious in a way almost impossible to comprehend. If false, it means civilizations exist, but are hidden, destroyed, or simply ignoring us. As you drift tonight, imagine the galaxy as a vast ocean. Billions of stars like islands scattered across the dark. Somewhere out there, perhaps, are other lights, other minds staring back at the same mysteries. And yet, for now, we hear nothing but silence, like waves fading into the night. The Fermi paradox is not just about aliens. It is about ourselves, our place in the cosmos, our future, and our fragile hope that we are not alone. The silence of the stars is both a question and an answer, both comfort and ache. And so, as the night deepens, we leave Fermi's question echoing softly, where is everybody? In the next section, we'll dive into a paradox closer to home, one born from Einstein's theory of relativity, where two twins part ways and return to find time itself has betrayed their bond. The twin paradox, when time splits between siblings. Imagine two twins, alike in every way. Let's call them Myra and Saul. They grow up side by side, sharing birthdays, secrets, and the quiet rhythm of life. But one day, Saul decides to embark on a journey unlike any other. A spaceship waits, sleek and silent, capable of traveling close to the speed of light. Myra stays on Earth, watching her twin vanish into the stars. For Saul, the voyage feels like only a few years. The engines roar, the stars blur, and time inside the ship ticks steadily forward. But when Saul returns to Earth, Myra is older, much older. The siblings embrace, but the mirror of their lives is broken. One has lived decades, the other only years. This is the twin paradox, a thought experiment born from Einstein's theory of relativity. It reveals how time itself is not absolute, but elastic, bending and stretching depending on speed and gravity. According to relativity, the faster you move through space, the slower you move through time. To Saul, aboard the near-light-speed spaceship, the journey is brief. But to Myra, watching from Earth, many years have passed. When the twins reunite, their clocks, once synchronized, no longer agree. At first glance, the paradox seems to cut both ways. If motion is relative, couldn't Saul also claim that Myra was the one moving while he remained still? Shouldn't Myra be younger when Saul returns? But the symmetry is broken by acceleration. Saul's spaceship had to speed up, turn around, and slow down again. Those moments of acceleration mark Saul's path as different, giving the paradox its resolution. And yet, even resolved, the twin paradox leaves us with a feeling of unease. Time, the steady heartbeat of existence, is revealed as pliable, dependent on perspective. There is no single, universal now. Each observer carries their own clock, their own truth. As you drift tonight, picture yourself on Saul's ship. The engines hum softly. Outside, stars stretch into shimmering lines of light. Inside, your heart beats slowly, your watch ticks calmly. But on Earth, years are racing past. Children are growing, cities changing, oceans shifting. Time itself has become relative, fragile, unanchored. The paradox whispers something profound. Time is not a river flowing the same for all, but a fabric that bends, stretches, and folds. Each of us drifts upon it differently. And perhaps that is the most human echo of this paradox. Even without spaceships, we feel time unequally. A joyful day slips past in an instant. A painful hour drags on forever. Two people may share the same calendar yet live very different experiences of time. Relativity is not only cosmic, it is personal. Myra and Saul, reunited but unequal, remind us that time is not guaranteed to move the same for everyone. It is elastic, strange, and deeply mysterious. And so the twins embrace, one old, one young, a paradox turned real in equations and in heartbeats. From here, our journey will carry us into an even stranger puzzle, one where knowledge itself becomes a trap, and the promise of a surprise collapses under the weight of logic. The unexpected hanging paradox: can a surprise be predicted? A prisoner sits in his cell, waiting. One morning, the judge delivers a strange sentence. You will be executed at noon on a weekday in the coming week, but the exact day will be a surprise. You will not know until the hangman arrives at your door. At first, the prisoner is terrified, but then he begins to reason. He thinks it cannot happen on Friday. If he is still alive by Thursday evening, then the only day left is Friday, and the execution would no longer be a surprise. So Friday is impossible. Now he reasons further. It cannot happen on Thursday either, because if Friday is ruled out, then by Wednesday night he will know that Thursday is the only option. Again, no surprise. By the same logic, Wednesday is ruled out, then Tuesday, and finally Monday. The prisoner smiles, relieved. The execution cannot happen at all. But on Wednesday at noon, the hangman arrives, and the prisoner is genuinely surprised. The judge's words have come true after all. This chilling puzzle is known as the unexpected hanging paradox. It shows how logic, when twisted back on itself, can collapse into contradiction. On the surface, the prisoner's reasoning feels airtight. By eliminating each day, he concludes that the execution cannot occur. Yet the very certainty of that logic blinds him. The surprise comes precisely because he convinced himself it was impossible. Philosophers have debated this paradox for decades. Some argue that the problem lies in the definition of surprise. Others suggest that the prisoner's logic is flawed because he treats the week as if it can be reasoned backward, when in reality, knowledge unfolds forward, day by day. But perhaps the paradox is less about law and more about life. We often try to predict what lies ahead, to eliminate uncertainty, to reason away the unexpected. Yet life still finds ways to surprise us. Joys arrive unannounced. Sorrows strike without warning. Just when we think we've mapped the future, reality takes a different path. As you drift tonight, imagine yourself in the prisoner's cell. The days stretch quietly, one by one, each night filled with reasoning, with certainty, with comfort in your own deductions. And then in the stillness of a morning, the knock arrives at the door, a shock, a twist, an unraveling. There is something strangely soothing in this, that no matter how tightly we plan, the unknown keeps its mystery. That surprise is woven into the fabric of existence, impossible to eliminate. The unexpected hanging paradox whispers to us, the future will always hold secrets. And perhaps that is what keeps life vivid, even under the shadow of logic. And so the week ends. The reasoning dissolves. The prisoner is gone, but the paradox remains, a quiet riddle in the halls of philosophy. From here we'll journey into a paradox not of fate, but of probability, one that plays with chance, choice, and the strange twists of statistics. The Monty Hall problem, where the odds are never what they seem. Step outside on a clear night. Look upward. A dome of stars shimmers above you, scattered like jewels on black velvet. The darkness between them feels infinite, the silence unbroken. But here is the question, the paradox whispered in the quiet. If the universe is infinite, eternal, and filled with stars, Why is the night sky dark? At first, the reasoning seems simple. In an infinite universe, every line of sight should eventually land on a star. No matter where you look, your gaze should fall upon a glowing sun. The sky should blaze with light, as bright and unbroken as the surface of the sun itself. There should be no darkness at all. And yet the night is filled with shadow. The spaces between the stars are black, deep, and silent. This contradiction is known as Olbers' paradox, after the German astronomer Heinrich Wilhelm Olbers, who posed it in the 19th century. For centuries, the puzzle lingered. Some suggested that distant stars were hidden behind cosmic dust, their light blocked before it could reach us. But that explanation falls apart because dust itself, warmed by starlight, would eventually glow, filling the sky with light. The true resolution of Olbers' paradox came only with modern cosmology. The night is dark not because the universe is infinite, but because it is finite in age. The cosmos had a beginning, the Big Bang, 13.8 billion years ago. Light travels at a finite speed, so we can only see as far as light has had time to reach us. Beyond that horizon, the stars are invisible. And there is another reason. The universe is expanding. As space stretches, light from distant galaxies is redshifted, its wavelengths lengthened until it fades into infrared and radio waves, invisible to human eyes. The darkness of the sky is not an absence of stars, but a consequence of time, distance, and cosmic expansion. Still, Olbers' paradox carries a haunting beauty. Imagine, for a moment, that the universe were eternal and unchanging. Imagine a sky so crowded with stars that no darkness remained. The night would blaze endlessly, a sea of light without shadow. We would never know darkness, never see the quiet beauty of constellations glimmering against black. The night sky, as we love it, exists only because the universe has a history. As you drift tonight, let the paradox comfort you. The darkness above is not emptiness. It is a reminder of beginnings. It tells us the universe has a story, a first chapter, a moment of birth. Every shadow between the stars is proof that the cosmos is not eternal, but alive, expanding, and still unfolding. Perhaps that is why the night sky soothes us. It is not just dark. It is a lullaby written by the universe itself, sung in silence, woven in starlight and shadow. And so the paradox resolves. The night remains dark, but its darkness is full of meaning. Next, we'll drift not through the vastness of space, but into the strangeness of physics, where a mischievous little being seems able to break one of nature's most sacred laws. Maxwell's demon. Maxwell's demon paradox. Close your eyes for a moment and imagine a quiet room, sealed off from the outside world. Inside, the air is still. Billions of molecules, far too small for the eye to see, are darting and bouncing, colliding in a chaotic dance. Some move quickly, some more slowly, but together they form what we call heat. Now picture a tiny door in the middle of the room, so small it could only be crossed by a single molecule at a time. Standing guard at that door is a peculiar little creature, Maxwell's demon. It is not a demon in the sense of horns and shadows, but a thought experiment dreamed up by the Scottish physicist James Clerk Maxwell in 1867. Here is how the puzzle works. The demon has perfect vision and perfect reflexes. It watches every molecule, every flicker of motion, and makes a choice. When a fast-moving, hot molecule approaches from one side, the demon quickly opens the door, letting it through. When a slow-moving, cool molecule comes from the other side, the demon opens the door for that one too, sending it to the other chamber. Over time, the demon has separated the air into two regions, one hot, one cold. A temperature difference has been created out of nothing but information and cleverness. And here lies the paradox. According to the second law of thermodynamics, the universe always trends toward disorder or entropy. Left alone, differences smooth out, heat spreads, coffee cools, ice melts, stars burn out. Order collapses into chaos. Yet Maxwell's demon seems to reverse this law. By sorting molecules, it creates order from disorder. Suddenly, we have two chambers, one heating up, one cooling down, and no energy was spent, or so it seems. For decades, this puzzle unsettled physicists. Could nature's most sacred law, the inevitable increase of entropy, be broken by a watchful creature? Was chaos not as permanent as we thought? The resolution, discovered much later, lies in the demon's task itself. To watch, to measure, to decide, the demon must gather and store information. And information, it turns out, is physical. To record it, erase it, and act on it requires energy. That hidden cost restores the balance. The demon cannot cheat entropy after all because its own bookkeeping adds to the disorder of the universe. But even with the solution, the paradox lingers in our minds, whispering of strange connections. What is the link between energy and information? Does knowledge itself carry weight, heat, and consequence? Some physicists believe this puzzle hints at something profound. That information is as real as matter and energy, a fundamental part of the universe's fabric. Drift with this thought. Every memory you hold, every word spoken, every idea shared leaves a trace, not just in your mind, but in the cosmic ledger of entropy. The act of knowing is not weightless. It is woven into the laws of physics themselves. Maxwell's demon reminds us of the strange intimacy between order and chaos. It whispers that even the tiniest choices, the smallest divisions, ripple into the great balance of the universe. And it tells us that even in chaos, there is no escape from the law of time. Things fall apart, heat spreads, stars fade, and even information itself dissolves into silence. But isn't that a kind of comfort? To know that entropy is universal, that we are all part of the same slow unraveling. The paradox doesn't weaken the second law. Instead, it strengthens it, turning it from a simple statement about heat into a meditation about life, memory, and the limits of control. So, as you drift toward sleep, imagine the tiny demon at its door, working endlessly, failing endlessly, and reminding us that even cleverness must bow to the flow of time. Next, we'll journey into a paradox not of physics, but of infinity once again, one that stretches the imagination with a playful absurdity. The infinite monkey theorem. Picture, if you will, a room filled wall to wall with typewriters. Each one clatters softly, but not from human hands. Instead, a troop of monkeys sits before them, pawing at the keys with no sense of purpose or language. Letters scatter across the page in meaningless fragments, strings like XBLZGHF or ADQUP. It's noise, pure chaos, random ink pressed into paper. Now expand your imagination. What if these monkeys kept typing not just for days or years, but for eternity? What if, given infinite time, they typed forever? This is the heart of the infinite monkey theorem, a paradox that blends probability, infinity, and a dash of humor. The claim is simple. Given infinite time, a monkey randomly striking keys will almost surely produce the complete works of William Shakespeare. Every sonnet, every play, every single word in perfect sequence. It sounds impossible, absurd even. How could nonsense, typed at random, ever give rise to Hamlet's soliloquy or the delicate rhythm of a Shakespearean sonnet? And yet, in the mathematics of infinity, it becomes not only possible, but inevitable. Why? Because in an infinite span of time, every possible combination of letters must eventually appear. Chaos, stretched long enough, births order. Gibberish becomes poetry. Randomness gives rise to structure. The universe, patient and eternal, writes itself into meaning. But the paradox lingers in how we feel about it. Imagine watching the monkeys type. For years, nothing but nonsense. For centuries, nothing but gibberish. For millennia, still nothing. The odds of producing even a single line of Shakespeare by chance are astronomically small. The probability is so close to zero it feels indistinguishable from impossible. And yet, stretched across infinity, even the impossible becomes certain. This paradox isn't just about monkeys and typewriters. It's about the strange relationship between chance and inevitability. It asks us to hold two ideas at once, that the likelihood of meaning is vanishingly small, and yet given infinite time, meaning becomes unavoidable. Think of it another way. Every phrase you've ever spoken, every sentence ever written, every dream ever dreamed, all of it already exists in the space of possibilities. The monkeys, in their eternal typing, will eventually find them all. Somewhere in the infinite library of chance, there is a page where your life has been spelled out word for word. And so this paradox becomes strangely poetic. It suggests that order is hidden in randomness, waiting to emerge. It hints that the difference between chaos and meaning is not absolute, but a matter of time, scale, and patience. Some philosophers take the idea further. They ask, if infinite monkeys can write Shakespeare, what might infinite universes create? Could there be, out there in the vast expanse, a world exactly like ours with you sitting here, listening, drifting toward sleep? And another world where everything is the same, except you chose coffee instead of tea this morning. Infinity doesn't just produce Shakespeare, it produces every possibility. And so, as you sink deeper into rest, imagine those monkeys typing in the background of eternity. Their chatter is nonsense, yes, but hidden in it is everything. Every truth, every lie, every dream. Chaos itself, when stretched across forever, writes the story of us all. Next, we'll wander into a paradox not of infinity or probability, but of perspective and knowledge, a puzzle that asks, what does it mean to know when your memory is rewritten? This is the strange world of the Sleeping Beauty paradox. The Sleeping Beauty paradox. Imagine, if you will, a quiet room where a woman sleeps peacefully. Her name is Sleeping Beauty, though not the fairy tale princess of old, but the subject of a curious philosophical experiment. Here is the setup. On Sunday night, Beauty is gently put to sleep. A fair coin is flipped. If the coin lands heads, she will be awakened briefly on Monday, interviewed, and then sent back to sleep until Wednesday, when the experiment ends. If the coin lands tails, she will be awakened on Monday, interviewed, then put back to sleep, and her memory of the awakening will be erased. On Tuesday, she will be awakened again, interviewed again, and then finally sent back to sleep until Wednesday. Now here comes the twist. Whenever she wakes up, Beauty has no memory of the previous awakening. For her, each awakening feels the same. She doesn't know whether it is Monday or Tuesday. She doesn't know whether the coin landed heads or tails. All she knows is that she is awake. The question she is asked upon each awakening is simple, but devastatingly tricky. What is the probability that the coin landed heads? At first glance, it seems obvious. A fair coin has a 50-50 chance. Heads or tails, equal and simple, why complicate it? But then the paradox sets in. Consider what Beauty actually experiences. If the coin landed heads, she is awakened once. If it landed tails, she is awakened twice. From her perspective, there are twice as many chances to find herself awake in a tails world as in a heads world. Doesn't that mean the probability should be 1-3 for heads and 2-3 for tails? This debate splits philosophers and mathematicians into camps known as halfers and thirders. The halfers insist the coin was fair, and the probability remains 50%. The thirders argue that Beauty must account for the fact that she is more likely to wake up in a tails scenario than in a heads one. And so the paradox remains unsettled. It asks us to think about probability not as something fixed, but as something shaped by perspective, memory, and observation. What does it mean to assign likelihood when your own experiences are incomplete, when your memory is unreliable, when reality itself is hidden? In a way, the Sleeping Beauty paradox mirrors life itself. We awaken into a world without full knowledge. We do not know all the conditions, all the hidden flips of the cosmic coin. Our memories are partial, our perceptions incomplete. Yet we still must make sense of probability, of what is likely, of what paths may unfold. As you let this puzzle drift through your mind, consider the gentleness of its lesson. Certainty is rare. Memory is fragile. Perspective matters. And sometimes the most honest answer is not heads or tails, not 50 or 33%, but simply, I do not know, and that is okay. So as beauty drifts back to sleep, uncertain of what day it is, uncertain of what coin was flipped, she becomes almost like us, dreamers waking in a universe without full memory of how it began, uncertain of how it will end. And yet, even in uncertainty, there is peace. Next, we'll shift from memory and probability into the fabric of logic itself, where one of the strangest contradictions emerges, Russell's paradox, the set of all sets that do not contain themselves. Close your eyes and imagine a vast library, but not a library of books. Instead, it is a library of sets, neat, orderly collections of things. Some sets are simple, the set of apples in a basket, the set of stars in a constellation. Others are more abstract, the set of all prime numbers, or the set of all ideas you've had before falling asleep. At first, the world of sets feels safe, logical, and infinite. But in 1901, the philosopher and mathematician Bertrand Russell stumbled upon a puzzle that shook this perfect world apart. He asked, does the set of all sets that do not contain themselves contain itself? Let's break it down gently. Some sets do not contain themselves. For example, the set of all cats does not contain itself, because the set itself is not a cat. The set of all chairs does not contain itself, because the set itself is not a chair. But some sets do contain themselves. For instance, the set of all abstract ideas is itself an abstract idea, so it belongs to its own collection. Now imagine creating a special set, the set of all sets that do not contain themselves. Seems straightforward, doesn't it? But here comes the paradox. If this set contains itself, then it shouldn't, because it only includes sets that do not contain themselves. But if it doesn't contain itself, then it must, because it belongs to the very group of sets that do not contain themselves. Either way, contradiction. The set both belongs and does not belong. Logic loops back on itself, like a snake swallowing its tail. Russell's paradox wasn't just a clever puzzle. It revealed a deep flaw in the foundations of mathematics. At the time, many believed that all of math could be built on the solid ground of set theory, but here was quicksand right in the middle of the foundation. A contradiction at the very base threatened to collapse the entire structure. The fallout was immense. Mathematicians scrambled to rebuild. New systems of logic were created, rules tightened, and restrictions added, all to avoid the infinite regress of Russell's paradox. It gave birth to whole fields of mathematical philosophy and reshaped our understanding of logic itself. But beyond the technical fix, the paradox whispers a lesson about limits. Even in the cleanest world of logic, where everything seems ordered and precise, paradox lurks. The closer we get to pure certainty, the more we discover cracks where certainty collapses into contradiction. And perhaps that is the beauty of Russell's paradox. It reminds us that infinity is slippery, that self-reference is tricky, that logic is powerful but not invincible. Even the grandest structures of human thought carry within them the seeds of paradox, little reminders that perfection may be forever out of reach. As you drift into sleep, imagine Russell's library, endless shelves of sets, some containing themselves, some not, and one strange shelf that flickers, appearing and disappearing, both belonging and not belonging, forever suspended in paradox. Next, we'll turn from the realm of logic back to the cosmos, into the ultimate long-term puzzle of existence. The heat-death paradox. How can eternity end in silence? Close your eyes and imagine the far, far future of the universe. Not next year, not a billion years, but trillions upon trillions of years from now. Stars have burned out. Galaxies have dissolved. Black holes, once the most powerful engines of destruction, have evaporated into faint whispers of radiation. What remains is not a sky of light, but a dim ocean of particles, drifting aimlessly in a universe that has stretched itself thin. Energy is spread so evenly that nothing stirs, Nothing changes, nothing happens. This is the vision of the heat death of the universe, a state of maximum entropy, where all usable energy has been spent, and time itself seems to lose meaning. But here is the paradox. If the universe is eternal, if time stretches on forever, how can it ever reach a final, frozen silence? How can infinity end in stillness? The second law of thermodynamics tells us that entropy, disorder, always increases. Stars burn fuel, ice melts, heat spreads. Eventually, energy differences smooth out until nothing remains to power change. In this view, heat death seems inevitable. The universe becomes a cosmic graveyard, perfectly balanced, perfectly still. And yet eternity resists endings. If time is infinite, won't fluctuations eventually happen? Won't randomness, given endless opportunities, produce tiny sparks of order again? Might particles cluster for an instant, creating something like a star, or even something stranger, a brief consciousness, flickering into existence out of chaos? Physicists call these strange possibilities Boltzmann brains, hypothetical minds that pop into being from random fluctuations, only to dissolve moments later. In a heat-dead universe, such bizarre events might actually be more probable than a universe like ours. This leads to a haunting question. How do we know we are not already such fleeting fluctuations, dreaming a reality that vanishes the moment we wake? The paradox deepens. If the universe has already lasted for eternity, why are we not observing it in its heat-dead state now? Why do we live in a time of stars, galaxies, and energy? Shouldn't entropy have already flattened everything long ago? One answer is that the universe is not eternal after all, that it had a beginning, and it may yet have other endings besides heat death. Some theories suggest that expansion could tear the cosmos apart in a big rip, or collapse it back into a fiery big crunch, or even give rise to new universes budding from the old. But perhaps the most haunting possibility is that heat death is indeed our destiny, a future where silence reigns, where time loses its rhythm, where eternity becomes not an endless story but an endless pause. As you drift into sleep, let the paradox wash over you. Heat death is both an ending and not an ending. It is stillness inside infinity, silence inside eternity, a universe that never truly dies but never truly lives again. And yet, in the quiet, there is beauty. The stars we see tonight shine all the brighter knowing they are temporary. The moments we share carry more meaning precisely because they are rare. Entropy may win in the end, but it is the very existence of endings that makes beginnings so precious. So rest easy beneath the stars. They are not eternal, but neither are we. And in that shared impermanence there is wonder. Next, we'll leave the cold silence of the far future for a paradox of surprise and logic, a paradox of free will. Take a slow breath. Feel the air fill your lungs, then let it go. Did you choose to breathe just then, or did your body decide for you? Now think of this moment here, listening to these words. Did you freely decide to be here, or did a chain of causes long before you made the choice inevitable? This is the haunting paradox of free will. On one side, we feel free. Every day we make choices, to rise or sleep in, to drink tea or coffee, to speak or remain silent. Each decision feels like a tiny spark of agency, a moment where the future is open and we can shape it. Without this sense of freedom, life itself would feel hollow, even meaningless. And yet, science and philosophy whisper a challenge. Physics tells us the universe is governed by laws. Every atom follows a cause and effect chain, stretching back to the Big Bang. Neuroscience tells us that the brain is a machine of chemistry and electricity, neurons firing in patterns determined by genetics and experience. If every thought is the product of physical processes, then where is the room for freedom? The paradox sharpens. If our actions are determined, how can we be free? But if they are not determined, if they are random, how can randomness count as freedom? Determinism makes us feel trapped, like actors reading lines from a script written long ago. Indeterminism, on the other hand, makes us feel like dice rolling through chaos, actions without reason or control. Either way, the freedom we feel in our bones seems to dissolve under the weight of logic. Philosophers have wrestled with this for centuries. Some are compatibilists, arguing that free will can exist even in a determined universe. For them, freedom is not about escaping causality, but about acting in harmony with one's own desires and reasoning. Even if your desires are shaped by the past, choosing according to them still counts as freedom. Others are hard determinists, insisting that free will is an illusion. We are passengers in a universe that carries us forward, believing we steer, but in truth, we are carried. And then there are the mystics and poets, who suggest that freedom may not be about control at all. Perhaps freedom lies not in escaping causality, but in embracing it, in flowing with the river rather than fighting it. Science complicates things further. Some experiments suggest that brain activity predicting a choice begins milliseconds before a person is consciously aware of deciding. Does that mean the brain decides before the mind does? Is consciousness merely an afterthought, a narrator telling stories about choices already made? Or perhaps there is more still hidden. Quantum mechanics, with its uncertainty and probabilities, might offer a tiny crack in determinism, a place where chance flickers at the heart of reality. But does chance really rescue free will, or does it just add randomness to the script? The paradox lingers unresolved. Are we free, or are we bound? Perhaps the answer is both. Perhaps freedom is less about escaping causality and more about the perspective we hold. From one angle, we are bound by chains of cause and effect. From another, we are the living link in that chain, expressing causes as they pass through us. As you drift toward sleep, let the paradox soften. Whether you are free or determined, whether your choices are sparks of agency or echoes of physics, you are here now experiencing this moment. And that perhaps is freedom enough. The freedom to be present in the mystery, even if the mystery cannot be solved. Next, we'll bring our long voyage full circle with one final paradox, both playful and haunting, about surprise, knowledge, and the limits of logic. The stimulation paradox. Imagine for a moment that everything around you, the stars, the oceans, the sound of your own heartbeat, is not what it seems. That beneath the fabric of reality there is not matter but mathematics, not atoms but algorithms, not space but simulation. This is the simulation hypothesis, a modern paradox that asks, if civilizations can one day create virtual worlds so detailed that the beings inside believe themselves to be real, how can we be certain we are not already inside one? The argument goes like this. Advanced civilizations, given enough computing power, could simulate entire universes, down to the tiniest particle. Inside those universes, conscious beings, people like us, would live, dream, and ask the same questions we do now. If such simulations are possible, there might be many more simulated worlds than real ones. And if that is true, the probability suggests we are more likely to be simulated than original. But here the paradox deepens. If we are simulated, who are our creators? And if they too live in a simulated world, who created them? Does the chain stretch back forever, an infinite tower of realities, each one nested inside another like Russian dolls? Or does it end somewhere with one true universe that gave birth to all the rest? The paradox also asks us to rethink physics itself. Why does the universe seem to run on mathematical laws so precise, so elegant, that they resemble computer code? Why does reality have limits like the speed of light, or the quantum graininess of matter, that feel suspiciously like the resolution of a screen or the processing limits of a machine? Are these the fingerprints of a cosmic programmer? And then comes the strangest twist of all. If we are in a simulation, does it even matter? Does love feel less real if it is written in code? Do dreams lose their beauty if they run on circuits? Perhaps meaning is not diminished by the medium. A poem written with ink, pixels, or binary still moves the heart. Perhaps reality, simulated or not, is defined not by its origin, but by our experience of it. The simulation paradox leaves us with a final dreamy uncertainty. If we are simulated, we may never know. And if we are not, we may never prove it either. We are suspended between possibilities, free yet bound, real yet perhaps virtual, alive in a world that could dissolve into code the moment we close our eyes. And so, as our 2-hour voyage draws to an end, let this final paradox wash over you like a lullaby. Reality itself may be the greatest mystery. Perhaps it is solid, eternal, and real. Or perhaps it is fragile, flickering, a dream within a dream. Either way, you are here in this moment, resting in the wonder of existence. The paradoxes have stretched our minds tonight, from Zeno's arrows to Russell's sets, from infinite hotels to heat death, from free will to simulation. Each one is a doorway into mystery. Each one is an invitation not to solve, but to surrender. And now, as your eyes grow heavy, remember, you don't need the answers. You only need the wonder. Let the questions drift into dreams where they belong, and let the universe, whether code, chaos, or cosmos, hold you gently until morning.